So we're going to do a walkthrough now of assignment number 3. This is the specification. I'm going to look briefly at the skeletons, what little there are, and then we'll also take a look at the test cases. This assignment is going to give you a chance to put into practice a lot of what we've been talking about this past week with respect to C++, exception handling, and how to write strongly exception-safe code. It'll also give you a chance to get some practice with the rule of 5. Thus far, you really haven't had to do much work with constructors. We've basically ignored assignment and we've ignored copy construction in our scoped array and our simple array. And now we're going to go ahead and do the whole kit and caboodle. So you get a chance to do everything with this assignment, including the move assignment and the move constructor. So that'll be really fun. And this will give you a chance to have a leg up on a lot of people, because a lot of people don't understand how these things work or how to implement them. There was a good question on the Piazza forum this morning asking, why the heck do we need move in the first place? And I posted a link to a nice article that kind of goes into detail, but the Cliff Notes explanation is that to support pass by value semantics, and if you look at C++ STL, you'll see a lot of places where values are passed, or parameters are passed by value, and values are returned by value, and so on. And so one of the reasons why move semantics are important is they help the C++ compiler eliminate unnecessary temporaries that would otherwise need to be created and destroyed in order to support pass by value semantics. And if you go back and watch some of the early videos we did on C++ templates, I showed an example, especially the example where we talked about the simple string and the use in the pair template. And I kind of went back and forth and showed you the consequence of enabling move semantic optimizations versus the more traditional copy constructor behavior. And you can see that the overhead goes way down because the number of temporaries that are created goes way down. And so that's kind of the reason. It gives you, the programmer, more control over telling the compiler when it can optimize things to get rid of the overhead of temporaries that otherwise would be necessary. And that article I posted on my website should hopefully explain that. Another thing that someone asked, which I'll just go over briefly while I'm thinking about it, they asked about const. Why do we need const? And the reason, of course, is that you want to have the compiler be able to enforce the semantics of objects that are not intended to be changed. And probably the best example of this would be when you pass a const ref to a method. And when you pass a const ref, you don't want anybody to be able to change the value of that object. You're passing it by const ref, typically just as an optimization to tell the compiler, don't make a copy of this thing, don't make a deep copy, just pass a reference. So const ref ensures that your intent of not changing the parameter is enforceable by the compiler. And so if you were to try to do anything to that parameter that's a const ref parameter, the compiler would, if you try to do anything to that would end up changing the state of the object, the compiler will say, hey, sorry, you can't do that, that's against the rules. So I'll try to point this out as we look through some other examples, but in a nutshell, that's the reason why const exists. It's a way to document your intent and then to allow the compiler to enforce the intent so you can't make accidentally the wrong choices in your code. Okay, returning back to assignment number 3, I've given you a header file this time, which is ArrayList.h, and we're going to go look at that in just a second. And then I've given you a bunch of other things. I've given you some test programs, which we'll look at, and a bunch of other build stuff just to make everything compile and set up the dependencies correctly. As always, don't make changes to those build and test files, or chaos and insanity will result. The ArrayList.h file, which we're going to examine, contains comments and some specification of the methods and so on that you'll need to implement in the ArrayList.cpp file, which of course should go in the source directory, as we've talked about. And that will be a generic class that implements an array, which is kind of a stripped down version of a vector. And the couple things we're going to focus on here, first and foremost, you need to make sure that you implement the methods in a strongly exception safe type manner. And again, go back and watch all of our discussions about generic programming and exceptions from a week or so ago or earlier this week, and you'll get to see what I mean when I talk about strong exception semantics. You should also copy over your scoped_array.h and scoped_array.cpp files from assignment number 2, which you're just wrapping up, and use those to implement the scoped array, which you'll need to implement your array list. And make sure, of course, that before you do that, you've got everything working correctly for assignment number 2. And this is a common theme throughout our assignments. They build on each other. So assignment 3 is going to build on assignment 2. Assignment 4 will build on assignment 3, and so on and so forth. So each step along the way, you have to make sure that your code works properly. Otherwise, you won't be able to get to the next level. It's kind of like a video game. If you want to get to the next level, you have to win all the boss fights at the current level or whatever. As before, I'll send out a submission link to everybody. Thanks, by the way, to pretty much everybody in the class for filling out the form. That's extremely useful. I really appreciate it. I think a handful of people did not fill out the form, so they will not get comments back on their solution. Okay, so I think everybody in the class is an undergrad, so it just talks about that. And the same rules apply as always in terms of honor code and coding standards and so on and so forth. Okay, let's go ahead and take a look at ArrayList.h. And you can see that this is going to include scoped array. So you're going to use your scoped array class as part of the implementation of this class. And what it's going to do is it's going to provide a Java-esque like abstraction, which will implement an array list type of behavior. And so we're not actually implementing this with a linked list. It's just an array-based version that has list-like operations on it. And under the hood, you're going to implement it using the scoped array. But the way you're going to have to implement things like your copy constructor and your assignment operators and so on are to be done in a strongly exception-safe manner. And we've talked about what that means. That means that if an exception is thrown, no resources are leaked, number one. And number two, the object that you were working on is left in a pristine state. So there's no corruption, no side effects, no partial completion. It's an all or nothing kind of thing. And so you're going to have various operations here. We're expecting the types that you're giving here will have various kinds of operations. Okay, so if you take a look here, you have a default constructor, which creates an array list of size 0. We have a constructor that's going to take a size and a default value, and you can make that default value have a default. so if you don't do anything, it'll just basically be empty. But the size parameter, of course, is used to determine how big to make the array that you're allocating and stashing away inside your scoped array. We then have kind of the classic copy constructor, which takes a const array list ref. And this is a good example of what we were talking about before about constness. Obviously, we are intending that this not be passed by value. So we're just going to have the compiler pass a reference to the right-hand side, to the source that we're copying from. But of course, we don't want this method to be able to modify the right-hand side or the source. And so we define it as const. If we didn't put it as const, then someone might think, oh, I can make changes to this, and that would have unexpected side effects, which would be a bad thing. So that's the kind of the classic deep copy constructor that we know and love. You hopefully learned about that in earlier C++ courses when you probably learned about the rule of 3. The rule of 3 being copy constructor, copy assignment operator, and destructor. Now we're going to go ahead and do the rule of 5. So you'll also have to implement the move copy, or the move constructor, not the move copy constructor, the move constructor. And this is the one that's going to sort of lobotomize the parameter and will leave it an empty husk. And this, of course, has no exception or no except guarantee. So it's the no throw guarantee. It says this thing does not throw an exception. And of course, it won't throw an exception because it's just transferring ownership. It's not actually doing any copying. It's just doing a move. Then we have our classic deep copy assignment operator. And this is similar to the copy constructor, with the main difference being that it has to clean up the left-hand side, and then it's going to go ahead and take the right-hand side, make a copy of that, and then do a swap. So this is where you're going to have to go back and rewatch our videos where we talk about strong exception safety guarantees. And as you'll recall, once you know the pattern for this, it's paint by numbers, because all assignment operators look exactly the same, and they're really simple. And they end up with strong exception safety guarantees without having to worry at all about try-catch clauses in your code, which is really super cool. In fact, I should also mention that if you do things correctly, there should be no try-catch clauses anywhere in your implementation. Your code should be strongly exception safe without try-catch, which is kind of the best of all possible worlds. It's great. So this version of assignment does a deep copy, and then it returns a reference to itself. Make sure you check for self-assignment, of course, as you should always do when you're dealing with assignment operators. This here is the move assignment operator. So this does not do a copy. What this does is it takes the right-hand side, or the source, and it goes ahead and it steals its state and puts it into the left-hand side, and then has to, of course, arrange to release the left-hand side. And this is where you're going to get a chance to finally use those release and reset methods that are part of your scoped array implementation. You may have been wondering, when the heck would I ever use those? Well, now you get a chance to use them, and they're very cool. When this is done, you should leave the source to be completely empty, including setting its value, its size to 0. And we'll talk about that when we look at the tests in a minute. The move assignment operator also should not throw exceptions, so it's marked as a no throw or no except method. Then we've got a bunch of methods down here that are going to do various things to our array list. So we're going to be able to add elements to the array list. And this is something that I probably wouldn't have done. I'm not sure why it's returning this as a const ref. It's just returning it. What is it doing here? Oh, I see what it's doing. It's returning the array capacity. It could probably just return that as a uint32t. It doesn't really need to return it as a const ref. I'll leave it the way it is, but I inherited some of this code from the previous incarnations of the course, and I changed a few things to cover what we're discussing, but I left some of the stuff there just because I didn't want to change it. But this probably could also just be returning a uint32t, because that's no less inefficient than returning a const ref. Down here, we do the same thing, except here we're going to go ahead and provide a value that we're going to add. So you can see here, we're going to add this value, and then down here, we're going to add the value to the index. So this is going to go ahead and this add version is kind of like pushback on a vector. It's going to add it at the end, whereas this version down here is going to go ahead and add it at the index location. And I suppose if we were really cool, we would do the in-place optimization, but I'll skip that for now. We'll leave that as something for a future assignment. So that's what add does. There are two versions of add. One just adds it at the end, and it's kind of like a pushback, and the other add here will add it at some location. And you can see that what has to happen here is that you need to basically slide things down, because you're going to be putting it somewhere, and you got to open up space for it. And all of these things need to be written cleverly so that they don't end up exceeding the bounds of the array without reallocating it. So this is going to take a little bit of thought. These methods are actually a little tricky, and you'll have to think about how to do this correctly. And the test should help ensure that you do so. Clearing the array list basically leaves it empty. So you'll essentially reset its current size back to 0. Get, as you can see here, get is going to do a range checked access to the array. So in this case, we're going to pass in an index, which again could be a uint32t as opposed to a const ref, but we'll leave it the way it is for now. And it's going to give you back the element at that location. But if the index is beyond the range of the array, it's going to throw the out of range exception. So you'll get a chance to learn how to throw exceptions in your code as well. Here's another get version. that will go ahead and get the results here. And you can see this is the const get version, and this is the non-const get version. So obviously the const get version can only be used or needs to be used when you have const arrays, whereas this get version can be used when you have non-const array lists. And keep in mind that both versions of get do range checking. Then we also have equivalent implementations of operator subscript, one non-const, one const, and they'll end up doing the implementation in a way that will be non-range checked. So they assume you know what you're doing, as is often the case in C++, just like with vector and dec, where there's these subscript operations that are intended to mimic the semantics of the built-in C-style arrays, where they don't do any range checking whatsoever. So these will be a little bit lighter weight, but of course you have to know what you're doing. You would typically use the subscript operations in situations where you're doing something like iterating through the array from beginning to end, so you always know you're in bounds, whereas you'd use the get operations if you don't know if your index is in bounds. So it's just a way to optimize things. It's very C++-like philosophy of zero overhead abstraction. We have an isEmpty method that just checks to see if the number of elements is 0, and I mark this with the no discard attribute to indicate you need to check the result that comes back from isEmpty. We have a method called remove, which will go ahead and get rid of the element in the array and shift it down so it'll compact it to take up the space for the element we removed. And you can see that when we remove an element, we also return a copy of it. And that's actually an interesting thing to discuss, whether that's exception safe or not. And we'll talk about that later, but let's assume for sake of argument that this will be okay. Here's the set operation. Set will basically go ahead and do a range checked set, very much like we have a range checked get. And so in that case, if it's not in bounds, it'll throw an exception. We have a size method that will return the size of the array, which is also marked as no discard. And then the final public method we have here is the famous swap method. And swap, of course, is what's going to be used by your copy assignment operator in order to do the pattern for strongly exception safe assignment. And so we'll end up using it to swap the contents of the right-hand side of the source array with the current left-hand side caller. And as you can see here, this is also marked as no except. You're not going to be throwing exceptions in swap. And if an exception is thrown in swap, it's the end of the world. So you'll need to avoid that. Then down here, we're going to have a wrapper around our physical buffer. And as you can see, this is going to be the scoped array that you implemented before. So please make sure you've got it working. And you'll need to use a bunch of its methods in this particular implementation. So make sure you've got it working correctly and that you understand how it works. Then we have two other data members, size and capacity. You might say, what's the difference between size and capacity? Capacity is the number of elements that are stored in the scoped array. So if you start out and you give the array list the size of 100, then capacity will be 100, and that'll be the size of the buffer that's stored in scoped array. Conversely, size will start out at 0, and every time you do the add call that does an equivalent of a pushback, it'll increment it by 1. And so size is what you're going to use for doing range checking, but capacity is what you're going to use to see if adding something new to the array will cause it to not have enough memory in it, in which case you have to regrow it. And if you take a look at the comments, they explain to you the logic for regrowing the array. Okay, and then at the very end of this thing, we are going to include ArrayList.cpp. If we come over here and we look at the source folder, you'll see it's currently empty. And that's because you have to put two things in there, one of which is, of course, your scoped array.cpp implementation from assignment 2. And the second will be your implementation of all these methods for assignment 3. So you'll have to write that .cpp file. And that'll just give you some more practice at writing the code correctly. And it should be fairly straightforward. The hard part's going to be implementing some of these methods, which are tricky. So you'll have to think about that. Now, to make sure that your code actually works correctly, we have a test program that's provided out of the box, and it will exercise a lot of the features, all the features that you're intended to implement to give you a sense of what the semantics should be. And I think it should be fairly straightforward. So for example, if you create an array list, then by default it's empty if you don't give it a parameter with the size, and the size should be 0. If you create an array list with 20 elements, then its size should be 20. You can go ahead and create an array list with size 20 and then give every element this default value, which is -1, 2, 3, 4, 5. And then of course, if you do that, then you should be able to get these semantics working here. And this is a good example. We could probably, since we're going through the range, we could probably go ahead and not use the get method, but we could use subscript instead. But I'm just doing this test to make sure your code is working properly. Down here, you can see we're using the copy constructor, where D will now become a copy of C. So it should contain the same size and the same contents that the array C had. Down here, we're making E by doing a move of D. So now we're taking the contents out of D, we're transferring the ownership over to E. So as a consequence, E will now have all the same state D did, but after doing the move, then D will have the size of 0 and will be empty. So that, make sure that that's what you do with your, excuse me, make sure that that's what you do with your move constructor. Down here, we then also illustrate the use of the move assignment operator, where we're going to take E and then move it back into D. So now that will correctly clean up D before it does the move, and then it goes ahead and moves E to D. So now D will have the same contents that E had, and E will become empty. And then the last thing we do here is we just chain a whole pile of these things together and set them all to 0. So that's just a way to test for that feature. There's a bunch of other code down here where you can see how we're doing the add method and the assignment method. So you can see that we're going to go ahead and create initially empty array lists, and then we're going to use the add method kind of as a pushback on a vector, and it's going to go ahead and put all these elements into the vector, into the array list, and then we'll check each time to see what the results are. And then we're going to go ahead and iterate through this thing and do a bunch more adds. We then do our assignment operation. This is the copy assignment. And then we test the index operation. And as you can see here, that should work correctly if you've done it right. Those shouldn't be too hard to implement. There's also some stuff here using size and add as we add elements in here to make sure that they are the right size. And then there's add and get. So again, we're just going through all the different permutations of things. Add via index. So in this case, we're going to go ahead and add a bunch of elements first, expanding the array. And then we're going to go ahead and use the add version that will kind of work like a range checked subscript operation to go ahead and put right elements over the ones that are already there. And down here, we go ahead and do some stuff with the get method to make sure it works. We test out const get to make sure that that works correctly. Some more get stuff. We check out empty. We do a bunch of things with remove. And this is fun because this will also give you a chance to test out some of your exception handling code. So you can see here that we go ahead and make an array of size 20, and then we go through here and remove some elements and show that the array shrank and that the values have been properly copied down to keep the range contiguous. Then we attempt to remove an element that's not in the array. We remove element index 22, and we only have 19 elements in the array. So that should throw the out of range exception, and you should be prepared to throw that, and then we show what happens when you catch it. Then I have a little test for swap, and swap, of course, is going to ensure that when you swap one array's contents with the other, they end up with everything shifted over, or not shifted over, swapped. We do some more remove operations here, do some more clear operations, and this also will demonstrate some of the exception conditions here. So if you clear an array and then you try to remove something from it, you should get an exception because there's nothing in it. So that's basically it. I think you'll find this assignment is substantially more complicated than the previous two, but it's also very satisfying because this will give you a chance to try out all the cool stuff that you've learned about C++ and the rule of five semantics and strong exception safety and so on and so forth. So I strongly encourage you to spend some time thinking about this. Go back and watch the corresponding videos that we've talked about these features, especially in my overview section on generic programming and exception handling. Those will be very valuable to look at. And I think if you do that, you'll find that it's pretty straightforward, but you'll have to do some extra work to make sure all the semantics are correct. And for things like adding elements or removing elements, you got to be very careful of fence post errors. And you may even want to add a little, feel free to add some private helper methods if it'll make your implementation easier for doing things like removing and adding. That may be a useful thing to do as well.